Good morning, boys and girls. And here we go again, another day working with derivatives. And today we're going to talk about what the derivative tells us about our functions. And we're going to learn specifically about the first derivative test. All right, here. So I have a function drawn for us. And we're going to just first talk about what does it mean for a function to increase or decrease. So usually I open this question up to the class, so think to yourself a little bit, what do you think that it means for a function to increase or decrease? How do you know if a function is increasing or decreasing? As we're looking at this, most people tend to say that, a function is increasing as the values get bigger. And I got a problem. What values? Well, as the y values get bigger, the function is increasing. The second we hit a max point, yesterday we talked about relative maxes. As soon as we hit this max point, then the function starts to decrease, right? And it's decreasing when the y values are getting smaller. And so that's one way we could define increasing versus decreasing. And that's one place we can look for between, our maxes and mins. It's when it changes from increasing to decreasing or decreasing to increasing, we have a minimum value. But we need to have another way to talk about increasing and decreasing. Now, another way to attack increasing versus decreasing is to look at the slope of the tangent line, okay? Where the function is increasing, if you kind of imagine these tangent lines, I'll draw a few of them, right? Where the function is increasing, you'll notice that all those tangent lines have a positive slope. And then as soon as my function starts to decrease somewhere, these tangent lines have negative slope, right? So that's another way for us to define increasing versus decreasing. So a function is increasing where its slope or derivative is positive, and a function is decreasing where its slope or the derivative is negative. Okay, that's something that we are going to want to learn and something we're going to relate to the first derivative test here in a second. Also, the thing we want to emphasize here is that, again, mins and maxes don't necessarily happen just where the derivative is zero. That's where we want to look because that's what happens when you change from positive to negative, right? When the derivative changes from positive to negative, it has to hit zero. But where you have this change in sign, okay? I have to have a max where it's going to change from a positive slope to a negative slope. And I'm going to have a min when it changes from a negative slope to a positive slope. Kind of a good example for this is like y equals x cubed. If I were to take the derivative of that, I get y prime equals 3x squared. And if I set that equal to 0, I do find that, hey, x is going to equal 0 at 0. So if I go and look, though, at x cubed, you don't necessarily have a min or max. Just because it equaled 0 didn't mean there's a min or max. There is no, in this case, the derivative is always positive, so the function is always increasing. Okay? So those things we can kind of learn here. So all that pretty much sums up what the first derivative test is. If f prime is positive, I know that f of x is going to increase. If the derivative is positive, I know that my function is increasing. If f prime of x is negative, then I know that f of x is decreasing. Okay? If my derivative is negative, then the function itself has to be decreasing. We can then use that and apply it in the fact that if f prime is changing from positive to negative, then the function is changing from increasing to decreasing, and therefore that means there must be a local or relative max there. And if my derivative is changing from negative to positive, then that means the function is changing from decreasing to increasing, and there must be a local min there. Okay? That's what the first derivative test tells us. That's what, when we look at the first derivative, those are the things that we should know. Okay, so on number 1 here, what we want to do is we want to find out when this function is increasing and decreasing. So if I want to know when a function is increasing and decreasing, what I'm going to do is I'm just going to go ahead and find the derivative of the function. In this case, some easy peasy power rule, right? And then I'm going to set it equal to 0 to find that critical value. In this case, we get x equals 0, so that's where, again, I should be changing, or where exciting things are going to be happening. I possibly could be changing sign in my derivative. And then all we then go and do is we create a number line to see. So 0, I'm going to put my critical point right in the middle, or right on my number line, and I'm going to test values to either side. If I were to take a number that was less than 0 and plug it back into the derivative, -3, then the derivative would be negative. I don't really care what my answer is. If I plugged in -3, I'd get -6. I just care about the sign. And so since when I plug in I get a negative answer, that's going to be negative on that side. And if I were to plug in a number bigger than 0, like 10, if I plug in 10, 2 times 10 is 20, that is going to be positive. So what that tells me is that the derivative is negative to the left of 0, and the derivative is positive to the right of 0, telling me that it is decreasing on the interval -infinity to 0, and then that it is increasing on the interval from 0 to infinity. Okay? And because I'm changing signs here at 0, I should have a relative minimum value because I'm going from negative to positive. And if we think about this graph, what it is now, again, this is a fairly easy one, but this is x squared minus 16. So x squared minus 16 would look something like that. And so, oh, that makes sense. We are decreasing to 0, and then we're increasing from 0 on, and we have a relative min at 0. All right here. And let me just show you something on the calculator. Give me 1 sec. Okay, I've plugged our two equations here, f of x, x squared minus 16 into the calculator, and its derivative 2x. And we want to look at these graphs just superimposed upon each other. And there they are. And so again, what we can kind of see, the relationship between these two things. When the derivative is negative, then f is decreasing. And when the derivative is positive, f of x is increasing. And when it changes from negative to positive, we have that relative minimum value right there. Okay? That's what we're kind of showing with all of our algebraic work. Okay, so here's another function, same idea, although this one's going to be a little bit more exciting. All right? We want to know, again, when this is increasing and decreasing. So, f prime of x, I'm going to find the derivative first, to do my first derivative test, 3x squared plus 4. I want to set that equal to 0 to find the critical values. Again, where it's 0 or undefined. So far, all these have just been 0, not undefined. So we get 3x squared equals -4. And then divide both sides by 3. And I get x squared equals -4/3. All right. And then, so I go to take the square root of both sides. And I can't take the square root of -4/3. That's really weird, right? That's going to be imaginary. So now I got to think about what's going on. If this doesn't equal 0, right? Then I got to go back up here. That means this is going to be the same all the time. And if I look at this, 3x squared plus 4, we get no critical values on this thing. 3x squared plus 4 is always going to be positive, which tells me that this function is always going to be increasing. All right? So this would be increasing from -infinity to infinity. All right, and again, so if we look at our graph here then of the two functions, y1 is x cubed plus 4x, and y2 is 3x squared plus 4. If we look at these, we'll graph this time, here comes f, and here comes f prime. Because the derivative is always positive, f was always increasing. And again, because it's always increasing, then there is no relative maxes or relative mins, because we don't have that change in sign. All right, next example here. Again, finding where it's increasing, decreasing. So if it asks, again, you want to get in your head, whenever it asks about increasing, decreasing, we are always going to look at the derivative. So f prime of x equals 4/3 x minus 1 would be to the 1/3. All right, I want to set that equal to 0. Right? And so I would get x to the 1/3 equals 0, or I guess this is going to happen when, raise both sides to the third power. It's going to happen when x equals 0. So I have a critical value. I'm going to do my number line, put 0 in the middle. If I test things to the left, if I plug in a negative number, remember x to the 1/3 means the cube root of x. So if I plug in do something that's easy. If I plug in -1, the cube root of -1 is -1. -1 times 4/3, I should write this down, f prime of -1, is 4/3 times -1 to the 1/3, or this is going to be -4/3, or again, I don't care about the number so much, just the sign. It's going to be negative. And then if I plug in a positive 1, now the cube root of 1 is 1. 1 times 4/3 is 4/3, so that's going to be positive. So that tells me that f, the function, is going to be decreasing on negative infinity to 0, and it's going to be increasing on 0 to infinity. All right. Real quick, we need to have a quick chat about our inclusion symbols here. If you'll notice, if we scroll back to the very first example we did, I included 0 here, right, on this one here. And then over here, now I did not include 0. This really kind of depends on the definition of increasing and decreasing you're using or what your book is using. AP will accept either way, and that's why I kind of flip-flop back and forth right here. Our book, however, the definition that we are using, they will not include the endpoints for increasing, decreasing. Okay, so I'm going to try to be consistent with the book and not do that. But it really just kind of depends on the definition being used. On the AP forum with AP teachers and calc teachers and college professors, they tend to lean more on the side that it should be included, mathematically speaking, but it's a giant debate in the mathematical world whether those are brackets or whether those are parentheses. Okay, our book is going to have it like that, so I'm going to try to be consistent with our book from here on out. Now you're probably asking yourself, Mr. Char, why do we do all that other, derivative stuff if they're always going to be so easy to take and, fun? Well, because they're not always going to be that easy. Here's one, I think it's a little bit more fun. Again, we want to know with increasing, decreasing, so I'm going to look at the derivative. In order to take this derivative, you need to use the product rule. Derivative of the first times the second plus the first times the derivative of the second. When I'm taking the derivative of the second, I can't forget that, hey, I've got an inside function, so I need to use chain rule. E to the u, e to the negative x squared over 2, times u prime. The derivative of negative x squared over 2 is negative x. And now I want to simplify this. E to the negative x squared over 2 plus, minus x squared e to the negative x squared over 2. And we're going to want to set this equal to 0 to find our critical values. All right, to solve these, to find your critical values, again, a common thing you're going to have to do is to pull out a GCF. So in this case, now I pulled out that e to the negative x squared over 2, and I'm left with 1 minus x squared. When I set the pieces equal to 0, the front term, e to the negative x squared, is an exponential decay function. And so that will never equal 0. It's got a horizontal asymptote at 0, so it approaches it, but it will never ever get there. So I kind of ignore that front part. I'm not going to have to really worry about it. What I really care about is this back part. Okay, I'm going to find out when that equals 0, and I get plus or minus 1. Drawing my number line now, I'm going to put a negative 1 and a positive 1. And I now need to test my intervals. When I plug in a number that is smaller than negative 1, like negative 5, if I plug it into e to the whatever, again, that's always going to be positive. E to any value is always a positive answer. So I don't really care about what number I get. I just want to know that it's always going to be positive. When I plug in negative 5 here, I get 1 minus 25. And 1 minus 25 is going to be negative. So I get a positive times a negative, which is a negative. If I plug in a value between negative 1 and 1, like 0, e to that's always going to be positive. 1 minus 0 is positive. And then again, the same thing, if I plug in something bigger than 1, like 5, that's going to be negative again. So now I can see where this function is going to be increasing or decreasing. So this is going to be decreasing from negative infinity to negative 1 and 1 to infinity. And then it's going to be increasing on the interval negative 1 to 1. And now I can also look where we have these sign changes. At the sign changes, I know I have some local min, local max values. I have a local min at x equals negative 1 because it changes from negative to positive. And I have a local max at x equals 1 because the derivative changed from positive to negative. If I needed to find out what the min and max value were, I would plug these back into the original function. All right. Thanks for joining me today, boys and girls. Have a good one. See you later.